Okay, good morning. Welcome to new lecture. In this lecture, I will continue about thermal stress. If you remember, as I mentioned, if we have one rod or any type of the structure, if we increase the temperature, we will have expansion. If we decrease the temperature from room temperature, we will have contraction. And any type of structure, for example, here, this rod, once it is free to move, free to deform, we will have deformation, we will see deformation, but we will not have any internal force or stress. And stress or internal force as a result of the temperature change is equal to 0. But in some situation, structure is not free to deform. For example, here, this rod, if I fix between two supports, if I increase the temperature, this rod wants to deform. If it is free, deformation will take place, and deformation delta will be alpha, thermal coefficient of expansion, times delta T, variation in temperature, times L, the length. So we will see deformation and internal forces and internal stresses are 0. But now if it is between these two supports, this rod wants to expand if I increase the temperature. Or if I decrease the temperature, it wants to contract. But it is not free to deform. What will happen? In that case, we will have internal forces inside of that rod, or internal stresses. So once it is free to deform, for example here I increase the temperature from T0 to T, the variation in temperature it is delta T. If it was free to deform, I can see deformation alpha delta T L. But now it is not free. So how I can find that internal force? It is easy to find. How? I will assume there is no support here in first step. So if we don't have support, what will happen? We will have deformation. We will have delta deformation. And as I mentioned, delta is equal alpha delta T L. Because of this deformation, this support will apply reaction after deformation up to here. Now the length, instead of L, it is L plus delta. Because of this deformation, we will have reaction in this support. That support reaction, it is unknown. I assume it is F unknown. That support reaction will return that to the initial shape. So it should apply force, and that force should deform this rod as much as delta in inverse direction. So if the initial deformation from left to right, then because of this reaction, deformation will be from right to left. And the magnitude of those deformations, they should be equal. So alpha delta T L should be equal to force times length. Here you can assume L plus delta, but because delta is so small, if we compare with initial length, you can neglect that and assume the length is L. So should be equal F times L divided by EA. From here F and L, from here L and L, from both sides they will cancel each other, and F force will be alpha delta T E A. So this is reaction. If we have reaction F here, definitely reaction here will be F, because summation of forces in horizontal direction should be equal to 0. They should cancel each other in order to have equilibrium. And internal force in any section we cut this rod, in any section we cut this rod, internal axial force will be equal to the F again. So because stress is internal force divided by cross-sectional area, and internal force N should be equal to the F, stress will be alpha delta T E A divided by A. From here, stress sigma will be alpha delta T E. So this is thermal axial force. This is thermal stress inside of the rod. Let's look at today two different examples with number, with dimension, real life problem. Assume we have composite rod. Composite rod means we have two materials. Part of this rod, the property, material property, it is copper. Another part, it is aluminum. So we have two different materials, and cross-sectional area is circular shape, so it is cylindrical shape. We have two rods. We attach here, we weld to each other, and we attach to the support as a fixed support. So part of this rod, it is copper, another part it is aluminum. And this length, it is 30 centimeter. This length, it is assumed 20 centimeter. As you see, the cross-sectional area, it is not equal. Copper cross-sectional area is bigger than aluminum. So assume a cross-sectional area for copper, it is 80 centimeter squared, and cross-sectional area for aluminum, it is equal to 20 centimeter squared. Room temperature, it is 26 degrees Celsius, and this assembly, it is in room temperature. Then, and once we have this assembly in room temperature, it is stress-free. There is no internal forces inside of this structure. There is no reaction. Everything is equal to 0. Then problem statement says the temperature drops. The temperature drops. How much drops we don't know, but temperature will drop delta T. Temperature drops, and the right support yields, right support, this support, I show with delta R, right support yields 0.025 millimeter in the direction of the contracting. So once we decrease the temperature, we will have contraction. The length will decrease. This support will move in the direction of contraction. How much it will move? 0.025 millimeter. Problem statement asks, determine the minimum temperature to which the assembly may be subjected. Determine the minimum temperature to which the assembly may be subjected in order that the stress in aluminum does not exceed 160 megapascal. So we want to find the temperature, how much we should drop the temperature in order the stress inside of the aluminum does not exceed from 160 megapascal. So we will drop the temperature. This support will move in the direction of contraction, and the deformation amount is given. Okay? We want to find this temperature variation so that the maximum stress inside of aluminum does not exceed 160 megapascal. Young modulus for copper, it is 100 gigapascal, and thermal coefficient of expansion for copper, it is 17 times 10 to the power of negative 6 per degree Celsius. Young modulus for aluminium is equal to 80 gigapascal, and thermal coefficient is equal to 23 times 10 to the power of minus 6 over degree Celsius. So, we want to find this variation in temperature. How I will find it? Let's assume this is free. If I decrease the temperature, I will have deformation. How much is that deformation? That deformation delta will be equal to alpha delta T L for aluminium plus alpha delta T L for copper. That will be equal to, if I plug these numbers here, I will have 17 times 10 to the power of negative 6 times the length for copper, 0.3 meter, 30 centimeter or 0.3 meter, times delta T plus alpha for aluminium, 23 times 10 to the power of negative 6, length 0.2 times delta T. This will be equal to let's see, I don't have the answer, or I have here. This will be equal to 9.7 times 10 to the power of negative 6 delta T. So if it is free, for example, we don't have this support, deformation from right to left will be this delta. Okay? So let's see what is happening. This support will move from right to left as much as delta R. So delta minus delta R, it is the deformation. This support reaction should return to the initial location. So, if it is free, it will move from right to left as much as delta, this delta. Because already support moves this much, delta minus delta R, okay, delta minus delta R, which is 9.7 times 10 to the power of minus 6 delta T minus delta R is given 0.025 times, if I convert to the meter, 10 to the negative 3. Okay, this deformation, this reaction will not allow to deform this much freely. So this deformation apply reaction here. So if I assume that reaction is F, problem statement says stress inside of the aluminium should not exceed from 160 megapascal. So if I assume this force is F, F divided by cross-sectional area of aluminium will be stress inside of the aluminium. If this is F, this force will transfer here, it will transfer here, and this support. So all internal force, it is F. F will be equal to cross-sectional area of the aluminum times stress inside of the aluminum. Cross-sectional of aluminum is given. The cross-sectional area of the aluminum was, here I remove it, it was 20 centimeter square. So 20 times 10 to the power of minus 4, I converted to the meter square, times 160 megapascal. So 160 10 to the power of 6 will be equal to 320,000 Newton. So this force we want to be 320,000 Newton. If I apply that force here, what will be deformation in entire assembly? Deformation in entire assembly should be equal to this deformation. I show this deformation with delta and this F, final deformation. Delta and this F is equal to deformation of, because of this force, F times the length of the copper, which is equal 0.3, divided by cross-sectional area 80 times 10 to the power of negative 4. A, this is E. E for copper, it is 100 gigapascal, plus the same F times the length of the aluminum part, which is 0.2, divided by the cross-sectional area for aluminum, 20 times 10 to the power of negative 4, times the E for aluminum. E for aluminum, I remove, it was here. It was equal to 80 gigapascal. So it will be 80 times 10 to the power of 9. That should be equal to this delta. That delta is 9.7, 10 to the power of negative 6, delta T minus 0.025 times 10 to the negative 3. Here F is known. I substitute F from here to here, and here I know the F. One equation, one unknown. The unknown is delta T. From here I can find delta T. Delta T will be equal to 56.2 degrees Celsius. So room temperature is 26 degrees Celsius. If we decrease that 56.2 degrees Celsius, temperature for that assembly will be negative 30.2 degrees Celsius. In that case, we will have stress inside of the aluminum, which is equal to 160 megapascal. So let's look at to another problem. We have a hollow steel cylinder. This is the black part, it is hollow steel cylinder. Surrounds a solid copper cylinder. So inside of this we have copper cylinder. Red will represent the copper cylinder. So the black one is the steel hollow cylinder, surrounds a solid copper cylinder, and assembly is subject to an axial load of 200 kilonewtons. Here at top we have one rigid plate, and here in the center we have rigid thick plate here, and in the centroid of this plate we have one axial load. The magnitude of that axial load, it is 200 kilonewton. Cross-sectional area for steel is equal to 20 centimeter squared, and for copper it is equal to 60 centimeter squared. Determine the temperature rise of entire assembly required to place all the load on the copper. Young modulus for copper, it is 100 gigapascal, and thermal expansion coefficient for copper, it is 1.7 times 10 to the power of minus 6 per degree Celsius. For steel, let's see, for steel, Young modulus is equal to 200 gigapascal, and thermal coefficient of expansion is 12 times 10 to the power of negative 6 per degree Celsius. We have one hollow cylinder. The hollow cylinder material, it is steel. We have Young modulus, we have thermal coefficient. Inside of that, we put one copper cylinder. Copper cylinder cross-sectional area is given, Young modulus is known, and thermal coefficient of expansion is known. Both length of these two hollow cylinder and solid cylinder are equal. It is 50 centimeter. At top we have one cap. Cap made using one thick plate, steel plate for example, it is rigid. In centroid of that we apply 200 kilonewton force. Then we increase temperature from room temperature. What will happen if we have this system? If we have this system, and assume we don't have that cap and force. Initially, the length is equal for hollow cylinder and solid cylinder, one of them from steel, another from copper. If it is free, we increase the temperature, both they will deform, we will have expansion. But because coefficient expansion for copper, if you look at here, if you compare, it is bigger than steel, the copper part will deform more than steel part. So if steel goes like this dashed line, here black dashed line, the copper part will deform more like this red dashed line. Now, if we apply force, and we want force only transfer to the copper, not steel, what will happen? If we don't have that force, that plate will come here. This will be the position of that plate. If I apply force, this copper rod will compress. It will squeeze that copper rod and it will deform down. If it deform up to here, exactly plate comes here. From here it comes up to here. All force will transfer to the copper. After that, if we increase the load, both will deform. The problem statement says force will transfer only to the copper. So what we should do, let's look at to the deformation of the copper under this load. Deformation of the copper will be, because we want all entire this force transfer here, will be 200 kilonewton times the length divided by E copper 100 gigapascal times 100 gigapascal times A cross-sectional area of the copper, it is 60 times 10 to the power of negative 4. The answer for this will be equal to 1.66 times 10 to the power of negative 4 meter. So this was centimeter square. If I convert to the meter square, it will be 60 times 10 to the power of minus 4. And this is 100 gigapascal. This is 200 kilonewton. So 30 comes because of that. This will be the formation of the copper under this load, axial load. If they are free, how much deformation we will have in both? If they are free, deformation inside of the copper will be length alpha 1.7 times 10 to the power of negative 6 times 0.5 alpha delta T L, this is L alpha delta T for copper, minus deformation for steel. So the entire deformation of the copper, because of that temperature change from here to here, I show with this one, we call it delta 1. Minus deformation of the steel, delta 2, because of temperature change will be thermal expansion coefficient. This should be 1.2 or let's see. I think this is, sorry, it is numerical mistake. This should be 17, not 1.7. This is 17. So here, this will be 17 times 10 to the power of negative 6 times initial length times delta T minus deformation of the steel because of the temperature change will be delta 2, will be alpha of steel 12 times 10 to the power of negative 6 times length 0.5 times delta T. This will be delta 2 should be equal to this delta. This delta is deformation of the copper under this axial load, which we have it is equal to 1.66 times 10 to the power of -4 meter. From here we have one equation, one unknown, and we can find delta T. So delta T will be 66.7 degrees Celsius. Let's explain one more time. We have hollow cylinder made using steel. So the material property for hollow cylinder, it is steel. We have solid cylinder. The solid cylinder material property is copper. Both length is equal. Both of them, they are 50 centimeter. So we put copper inside of the hollow cylinder, and you see the cross-sectional area for hollow steel is given, cross-sectional area for copper is given, Young modulus for both is given, thermal expansion coefficient for both is given. At top we have one cap, and in the centroid of the cap we apply 200 kilonewton force. We want to find temperature change so that all entire this force will transfer to the copper. So contribution of the hollow steel cylinder will be 0, and entire force will transfer to this copper. If we don't have this load, what will happen? If we increase the temperature, both this copper and steel, they will deform. We will have expansion, and because the thermal expansion of copper is bigger than steel, the copper part will deform more than steel part. So deformation for copper will be bigger than deformation for steel. So deformation for copper I show with delta 1. It is alpha L delta T for copper. Deformation for steel I will show with delta 2. Alpha of steel times L of steel times delta T of the steel. Because entire assembly we put in the same location, in the same environment, delta T for both, they should be equal. So both of them, the variation in temperature will be delta T. In order to transfer entire load to the copper, deformation in the copper should not exceed than delta 1 minus delta 2. So deformation in the copper should be equal to delta 1 minus delta 2. That deformation will be equal to force inside of the copper. Problem statement says entire force transferred to the copper times length divided by EA of the copper. Of course, I know maybe you will ask, now length it is not 50 centimeter, it is 50 centimeter plus delta. But as I mentioned, because that delta, if we compare with initial 50, it is very small, we neglect that part. So it is approximation, we neglect that small variation. So deformation in the copper should be equal to delta 1 minus delta 2. If we plug here, we will have one equation, one unknown, and that unknown is delta T. We can find delta T, so delta T will be 66.7 degrees Celsius. Thank you so much for watching this lecture. See you next session. Bye-bye.